Hello again. We're going to talk about aldehydes and ketones. And we're going to start by first talking about some of the common names of some of the more easily encountered ketones and aldehydes out there. All right, so the first one is the smallest member of the aldehyde family, only one carbon long. You have two hydrogens on that very same carbon. This is known as formaldehyde. And formaldehyde is a molecule that you actually use to preserve um, cadavers and preserve body parts. And it's because it is a really good molecule at killing any type of microbes that may be lurking around. And that's what allows it to preserve the body parts and cadavers. So needless to say, and as you can kind of see from the battle sign right here, yes, it is quite toxic to living organisms. The next one, which is one carbon longer than formaldehyde, is known as acetaldehyde. And this one, specifically, you encounter after drinking alcoholic beverages. Basically, in beer, wine, anything that's alcoholic, you do have ethanol, which is drinking alcohol, and that gets processed by your liver entering into acetaldehyde, and ultimately that feeling of hangover, as people describe, is as a result of the acetaldehyde, being accumulated in your system. So it is a little bit toxic. Other alcohols also undergo a similar type of reactivity, and they end up being more toxic. For instance, methanol, which is only one carbon long, going through this process will produce formaldehyde, which, as I just mentioned earlier, is really, really toxic for living organisms. So aside from ethanol, don't be drinking any other type of alcohol. All right. And another one that you might have heard of in the past, especially if you've been following the lecture series thus far, is this one right here, which is an aldehyde, but it's an aldehyde attached to the benzene ring. This is known as benzaldehyde, as a common name. And it does have a bit of an almond smell to it, and that's not a coincidence because it is actually found in almond oil. So, in case you ever wonder, yes, that's kind of what one of the sources are. Now, this one you've definitely encountered if you worked in a chemistry lab. This is a ketone. A ketone that contains three carbons in total. It is the smallest ketone that you can get, and this one is known as acetone. And it's one of the common solvents that we use in the laboratory to clean up glassware that contains organic, residue. Also, you might have encountered acetone in your daily life because it is one of the main components of nail polish remover, which is kind of funny because I do remember back in the day when my mom would actually be removing all the nail polish from her fingers, and I used to hate the smell of this thing. And nowadays, I've used acetone so much that I'm like, okay, it's not the greatest smell out there, but I'm like, yeah, okay, that's fine. That's fine. You get accustomed to it. All right, another one that we've talked about in the past is this acetone derivative, but in one side you have a phenyl ring instead of a methyl ring or a methyl substituent. This is known as acetophenone, and it is a liquid at room temperature. Mass-wise, it's not big enough for it to be a solid at room temperature. However, if you do replace the other methyl substituent with another phenyl, you get benzophenone, and this one has enough mass that it's actually a solid at room temperature. And this particular solid has the interesting feature that not only do you have the carbonyl, as part of the ketone, but you have actually plenty of conjugation as a result of the two benzene rings. So much so that you can actually create stable radicals with this molecule. So it is often used in chemistry as a visual guide to determine whether or not a solvent, so like this solvent right here, benzophenone has been added to. And in addition to that, you can see this big ball right there, which you may be wondering what that is. That's actually a ball of sodium metal, elemental sodium, that has been added to this flask for the sole purpose of completely reacting away any water that may have been present in the solvent. And the moment that the water is fully consumed, the residual magnesium, or not magnesium, but in this case, sodium metal, donates its electrons to benzophenone, creating this vividly, purple color radical. And that's kind of like the visual aid to tell you that, yes, your solvent is completely free of water. So yeah, this is something you would do in labs that require complete removal of water and no water whatsoever present. So kind of cool stuff. All right, so now let's talk about straight nomenclature using the IUPAC system. We're going to start with aldehydes. And the way we name aldehydes is to basically name the molecule like you would normally name your alkane derivative. But if it is an aldehyde you're dealing with, what you end up doing is you drop the E of the alkane name and you replace it with the suffix AL. And as far as the pronunciation, I'm going to get to that in a second, but you got to be careful how you pronounce the names of aldehydes. Now, before that, one more thing to mention is that if you do have an aldehyde attached to a ring, and the aldehyde will not be part of the ring, it will have by default to be, it will look almost like a substituent, but because it has no choice. One of the ends of the aldehyde has to be a hydrogen, so it cannot be part of the ring itself. But if it is connected to a ring, then you refer to this aldehyde as carbaldehyde as a suffix. So one more thing to also keep in mind, there is a functional group priority that now you have to be more on point about. To remind you about it, alkenes and alkynes are about the same priority, so they don't necessarily take priority over each other. They're about the same. However, when you compare them to alcohols, which are more oxidized than alkenes or alkynes, the alcohol takes priority. And if you extend that logic any further, your aldehydes are even higher oxidized versions of the same carbon component. So aldehydes take higher priority over all three of these functional groups. So that's how you ought to be thinking of them. So when you look at a molecule like this, the moment you recognize that an aldehyde is present, you gotta make sure that you cover the longest chain that does include that functional group of highest priority. So what that means is that although you might be tempted to say, well, the longest chain is all the way from the bottom carbon, the bottom methyl, all the way down here, all the way to the top methyl up here, sure, that is the longest chain, but that chain does not contain the functional group. So fortunately, that will not do. So you have to select the chain that is highlighted here in yellow to be the longest chain. And specifically, we're going with that one, which contains 1, 2, 3, 4, 5 carbons, as opposed to the opposite route, which would be 1, 2, 3, 4, 5 as well, only because the one that has been highlighted does have the most amount of substituents on it. So if you count them, you have 3 substituents, right? You have 2 methyls, and then you have 1 propyl substituent. Position 1 is automatically the carbonyl carbon where the aldehyde is located. So that means that propyl is at position 2, and the other 2 methyls are positions 3 and 4. So altogether, this is known as 3,4-dimethyl 2-propyl pentanal. And be careful how you pronounce these things. It's anal as far as how you pronounce the suffix. Don't don't confuse yourself into saying some obscenities as far as how these molecules are, represented. All right, let's do another example. All right, so now this one is an aromatic ring, and attached to that aromatic ring, you have your aldehyde unit. So here you have to recognize that this does have a common name. The common name of that aromatic aldehyde is benzaldehyde itself. And position 1 will be exactly where the aldehyde component is located, being that that's the functional group. Aside from that, we have a fluoro substituent, we have a methoxy substituent, and we have an isopropyl substituent. And it does work out that if you go in clockwise rotation from the position of the aldehyde, you'll end up yielding the lowest numbers for most of the substituents. So you'll have 2 for fluoro, 3 for methoxy, and then you have your 5 for isopropyl. And then at the end, you end up with benzaldehyde. Okay. Now, an example of a regular ring system that has aldehyde units hanging off of it is this one right here, and you happen to have 2 of them. So first you name the cyclic unit, which is cyclopentane, and on that cyclopentane, you have two aldehydes, but because they're attached to a regular ring, you have to end it with the name carbaldehyde. So this will be cyclopentane 1,3 dicarbaldehyde to emphasize that there are two aldehyde units present in the same molecule. Okay, and then one last example. If you look at this molecule, you should recognize that you have the aldehyde functional group, but you also have an alcohol functional group and then your alkene functional groups. So you have to pick the chain that has the longest amount of carbons that incorporates the functional groups. And if you have to give priority to one over the other, it better be the aldehyde in this case. So we're going to pick this particular route, right? Incorporating the carbonyl carbon and going all the way around, covering the alkenes and the alcohol subunits. So with that in mind, you should see that you have an ethyl substituent attached to the chain, a methyl substituent, and a propyl substituent. So as far as alphabetical priorities, ethyl goes before methyl, methyl goes before propyl. And as far as the functional groups, this is Al for the ending for the aldehyde, it's Ol for the ending of alcohols, and it's ene for the ending of alkenes. So as far as the name goes, you will name this 2-ethyl, 4-methyl, 5-propyl octane to incorporate the 8 carbon chains. And then notice that for the alkenes, the alkene that appears at position 4, the substituent that takes priority on the right side of the alkene is this one right here because it's closer to the oxygen. The priority group on the left side of this alkene is this one because it's an allyl versus just a regular propyl. So that's the Z configuration. The second alkene is straight out your trans configuration, so that will be just E. And then to finish it off with the suffixes, right, you still say octane to tell the whole size of the parent chain of the molecule. But as far as the substituents go, you have to list them. And I personally do this alphabetically. I've seen people do this a little bit different, in which they put the suffix of the priority group at the very end. But personally, just do it alphabetically. So it will be 1-al 4,6-diene to tell you that you have 2 alkenes, and then 3-ol for the name of this whole thing. Okay, now let's take a look at ketone nomenclature really quickly. We're going to basically do the same thing as before. We name the alkane like you normally would, but you drop the letter E from the alkane name and you replace it with the letters own, or you might be tempted to say one, but it's own as far as the pronunciation goes. And as far as priorities go, the ketone takes priority over the aldehyde in this respect, right? This is slightly more oxidized than the aldehyde itself. And I'm showing you here the oxidations just to kind of validate that point. All right, so here's a molecule, and you want to make sure that you pick the longest chain that incorporates a functional group. So that means that we're going to pick this particular chain. And out of that, we have a sec-butyl substituent and we have a methyl substituent sticking out. So the name of this molecule will be 4-sec-butyl because B is what we count for alphabetical purposes, not sec. And then that will be followed by 2-methyl. And as far as the chain length, we have 7 carbons, hence the name heptane. But we see that we have the carbonyls at positions 1, 2, 3, and positions 5. So this is 3,5-dione to tell you they have 2 ketones in the same molecule. Now for this cyclic molecule, this is cyclohexane, but we have 3 carbonyls, 3 ketones in essence, at positions 1, positions 3, and position 5. So this will be cyclohexane 1,3,5 trione. All right, and then let's do one more with a couple extra functional groups. Basically, the ring system is the parent chain that contains the functional group of highest priority. And the substituents are bromo, ethyl, and tert-butyl. So out of those ones, bromo takes priority. Then tert-butyl, because tert doesn't count for alphabetical purposes, and that's followed by ethyl. So we have 2 bromo, 5 tert-butyl, 3 ethyl, cyclohexane, and then we deal with the substituents, right? So position 1 is where the ketone is located because of the priority rule. That would mean that the alkenes are positions 2 and 4, So this is 2,4 diene, 1 one. All right, then we'll do one more, and this will finalize the video. Um, so we pick the longest chain that contains the functional groups, and right here we happen to have an aldehyde as well as a ketone. We wanna make sure that we give priority to the ketone. So notice that position 2 is where the ketone is located, meaning that the carbon on the very right is position 1. And of course, that means that the aldehyde gets screwed over in this sequence, but it's what it has to be because the ketone takes priority over the aldehyde. So other than that, you see you have your ethyl substituent, methyl substituent. So 4-ethyl, 6-methyl, 7 carbons long, heptane, 7-al, 2-one, to emphasize the functional groups present in the molecule. All right, so with that said, I'll catch you in the next video where we'll revisit some of the carbonyl chemistry that you have seen in the past, along with some spectroscopy. Okay, bye-bye.